So what I wanted to do was to go through some of these things. As you notice, there's those sulfide and sulfate and CO2 and SO2 and all of those reactions can be kind of tricky to balance. Okay, and so I want to sort of give you a scheme for how you balance redox reactions because it'll be useful for all of these. Okay, so let's jump into that. And before, let's look at the Alex report. So I do want to mention one thing. I sent an email out to 32 or 33 folks today who are showing a lot of this trending here. So the people that are bumping around here in this valley, those are the people who are not procrastinating. This gap here from the active work to no work, that's showing procrastination or cramming, I would like to say. And it's a terrible way to learn. So cramming things until the deadline is pushing everything into your short-term memory. So when you get to the test, you don't remember it. Okay, so taking things in smaller bites, like I've been preaching this whole time, is going to help you remember the material. And it's not just about getting the points, it's about knowing the material, because every one of your degree plans has required this course for a reason. They need you to know some chemistry because it's going to be used later. All of your disciplines will depend upon chemistry to some degree or more. And so you want to make sure you retain it after you get out of the class. If you're in the habit of waiting till the deadline to start your work, you're just using your short-term memory and you're not going to be able to remember that material later. So just a warning. So we're going to talk about redox reactions and balancing them. That's the main point of today. And then I'll hit a couple of other topics of interest. So this is what we use, these redox reactions and the activity series, to come up with voltaic cells. So these are our batteries. So this is like the guts of a battery right here. And so it's got the anode and the cathode and a little salt bridge here. And you've got copper in one solution and zinc in the other. You've got copper metal and zinc metal. And you just put this stuff together and it just spontaneously generates voltage. No moving parts. You just put the stuff together and out comes electricity. Why? Well, because of the activity series. The activity series is showing you that some metals push electrons differently than others. Okay, and so lithium being the most active element, it can push electrons harder than other elements. Okay, so here's the schematic of the voltaic cell showing the electron flow and the ion flow. So if you'll notice here, the electrons are flowing along with the negative charges. So the electrons are going from the zinc over to the copper. Okay, so here's the electrons. They're pushing on that voltmeter with 1.1 volts of electromotive force. And the anions are going in the same clockwise direction. You see the nitrate ions are going into the salt bridge here. They're going around the salt bridge down here, and they're coming out of solution here, those nitrate anions. Where are the cations going? Well, they're going the opposite direction. The sodium in the salt bridge is going to the right or counterclockwise. It's on the bottom of this loop. And then the copper ions are plating out on the copper electrode. Notice the direction that the cations are going. The sodium is a cation, the zinc is a cation, the copper is a cation. Where are they going? They're going towards the cathode. So the name cathode was given first. And then we discovered that cations, these ions that go towards the cathode, we call cations. So that's where that name came from. Cations go towards the cathode. Where do you think anions go? Towards the anode. So we had these macroscopic objects, these metal pieces. We called them the cathode and the anode, put them in solution, and the cations go towards those different electrodes. Okay. Now, if you'll notice here, this anode, the zinc anode, is silver colored, and the copper color for the copper cathode. And so once again, our memes are wrong. So the little silver guy is not the cathode; he's the anode. So he should be called the anode or the zinc anode, and the other one should be copper cathode. So I don't know if your cat's copper colored, but that would be a good name for a cat. Copper, yeah. Zinc, I don't know. That'd be okay cat name. But hey, zinc, what's up? And so they would say, you must be a chemistry major. So in these electrochemical processes, we use oxidation numbers, and that was the last Alex exercise, to keep track of what was oxidized and what was reduced. So looking at those oxidation numbers, if those oxidation numbers increase, it's being oxidized. Even if it's negative, if it's -1 and it increases to 0, it was oxidized. So that's another way to know what was oxidized and what was reduced, is if the oxidation number goes up, it's being oxidized. If it goes down, it's being reduced. But sometimes it's not easy to see because we've got all kinds of molecular and polyatomic ions involved. And so we can balance redox reactions another way that's just super simplistic and very procedural. And if you're like me, you like a procedure. Just tell me the steps to do, and I'll memorize the procedure, and it'll work every time. And that's what we have here. So if you follow these steps in order, this is super easy. So this is the half reaction method. So here's the procedure all on one slide. We break the reaction into 2 half reactions. Now that requires some looking at the reaction to kind of see what would be the logical breakup. Okay. And then we start balancing it. We balance each of those half reactions independently. So we do it in this order. If we look at the elements and they have like an iron or a manganese or something like that, we make sure we balance those elements first. So we get the same number of non-hydrogen, non-oxygen elements balanced first. So like if there's lithiums on both sides or irons on both sides, we get those to be equal. And then we start working on the hydrogens and oxygens, because those are the ones that really do a lot of chemistry. We have water, we have acid, all of those are different things. So we balance the oxygens by adding water. So let's say I had a MnO4 and an MnO2, and I've got 2 different values of oxygens. I need 2 more oxygens over here, so I add 2 waters. So I want to balance the oxygens, but I put a whole water molecule on it. And so we balance the oxygens by adding water. Then we've added hydrogens to the reaction, so we balance those using acid plus, so H plus acid protons. And we put those on the side, whichever side of the reaction we need to balance the hydrogens. And then we look at the charges. We haven't done this yet, but we add up all the charges on the left side of the arrow and the right side of the arrow, and whichever side is too positive or whatever, we need to reduce one so that they're equal. We add electrons to that side. So 4 steps: elements other than hydrogen and oxygen, then oxygen using water, then hydrogen using protons, and then balance the charge with electrons. Then we look at those electrons. One of those reactions is going to produce electrons, and the other is going to use electrons. And so whatever is produced needs to be completely used up by the next reaction. So if we have 3 and 2, then we're going to multiply the top one by 2 and the bottom one by 3, so that we have 6 produced and 6 used. Okay. If we have 2 on top and only 1 on bottom, we just multiply the bottom reaction by 2, so that 2 electrons are produced and 2 electrons are used up. And then we add everything together. Now, when we add all this together, we might have water on both sides of the reaction. Let's say we have 5 waters here and 2 waters here. We're going to subtract 3 from this side. And so, or we'll subtract 3 from both sides. And so we just have 2 on one side. Okay. So we'll just do an example. So this is a redox titration. So we have permanganate and oxalate. And this is a way to determine how much of this organic acid is in solution by titrating it with this purple solution of permanganate. So potassium permanganate is deep purple. And if we put a little bit of permanganate in the solution, it's going to react with the oxalate and it's going to go colorless. So if we drop some purple liquid in and there's still that acid molecule in there, that organic molecule, the permanganate gets chewed up as it eats up that organic molecule. And so we don't have any purple color. But as soon as we run out of the organic molecule, then we still have permanganate and it turns purple. So here we have a lot of organic molecules, so the permanganate's being chewed up. Here it's slower, but it still gets chewed up. And then a few drops after we pass the amount of oxalate, then the whole solution turns purple and we're done with the reaction. So here's our reaction. We've got the permanganate reacting with this oxalate. And I've deleted all the spectator ions. So this organic acid is called oxalate, and it just produces manganese ion, manganese 2 plus, and CO2, right? So can you see the two half reactions, right? The carbons go with the carbons. So this is one half reaction, and then the manganese and the permanganate is the other half reaction. So we separate those. We write a carbon reaction, and then we write a manganese reaction. So let's do the carbon reaction first, okay? So here we have C2O4, 2 minus, goes to CO2. So the first step was to balance all of the elements other than hydrogen and oxygen. So we have 2 carbons on the left and only 1 on the right. So we're going to add a 2 in front of that CO2. So that's pretty simple. Balance the elements other than other than hydrogen and oxygen. Now the oxygen is balanced. We got lucky. So we have 4 oxygens on both sides. Okay. So if we didn't have to add any waters, that means we don't have to add any acid protons. So we're set. The only thing left now is the charge. So we look on the left side and we see that there's a 2 minus. We look on the right side, there's 0. They don't have to both sides equal 0. In fact, you can't always do that. They just have to equal each other. So how do I get a minus 2 to equal 0? I've got to subtract 2 from the 0 side. So they're both equal to minus 2. So on the CO2 side, I'm going to add 2 electrons so that both sides is minus 2. So you see that? So now I can check my work. Okay, why did it jump to the next one? Let me go back here. Okay, so I've got a 2 minus here. This is minus 2 equals, and this is minus 2. So that's good. My charges match. Okay, and I've got 2 carbons on both sides. I got 4 oxygens on both sides, and we don't count the electrons. We're just looking at the charges for the electrons. Okay, so now let's look at the manganese half reaction. So MnO4 goes to Mn. So the elements other than hydrogen and oxygen are already balanced. The manganese is already balanced. So then we go to the oxygen. We need to add 4 waters on the right. So you see what I'm saying? I've got 4 oxygens, and I balance oxygen using water molecules. Now I've got hydrogens involved. So I balance the hydrogen by adding H pluses to the left side. Okay. So you see how it kind of builds. I had these 4 oxygens, and so that made me add 4 waters. And now I've got 8 hydrogens, and so I've got to add 8 H pluses. That's why I hold the charge balancing to the last, because I'm changing the charges and all of that stuff. It's got to do this in order. Yes?
Is the hydrogen on the left side always going to be aqueous, or is it going to be gas?
Which one?
Like
this one here?
Plus,
So if it's a plus, it has to be aqueous. Okay. Yeah, the only H gas would be H2 gas. Yeah, that's good. Yeah. And you never write water aqueous because it's already water, right? So water's always liquid or gas, but it was never water aqueous. So then to balance the charge, we add 5 electrons to the left side. Well, how did we get that? So let's look at this. So we had 8. We had a plus 8, and this is a minus 1. Has got to equal a plus 2. Okay, you see that? So we have on the left side plus 7, on the right side plus 2. So we got to bring that 7 down 5 units. And so that's how I know by adding electrons, I'm subtracting charges, right? So I'm bringing that plus 7 down to a plus 2. So that's where I get the 5 electrons. So now we can check our work. We have minus 5 for the 5 electrons, plus 8 for the H positives, and minus 1 for the permanganate, and that equals a plus 2. So that checks out. All my charges are balanced. Let's make sure our elements are balanced. So I have 8 hydrogens right here, right? The 8 hydrogens. I have 1 manganese. I have 4 oxygens. Over here, 1 manganese. 4 times 2 is 8 hydrogens, 4 oxygens. So it's balanced. So this is really good. You can always check your work at the end. If you have to have both balanced charges and balanced atoms for it to be a balanced reaction. But these are still half reactions. Okay, this is what the permanganate does. It oxidizes things, and so it's stealing these electrons from something, and it's being reduced. So the permanganate is being reduced. It's gaining electrons and being reduced to the manganese. The oxalate is being oxidized. It's giving up its electrons. It's losing electrons. And so now we put them together. So here was the oxalate reaction. It produced 2 electrons. The permanganate reaction required 5 electrons. And this is the redox handshaking that must take place. So we've got to get those electrons to equal each other. So we can't produce 2 if I need 5, right? So this is how we know how the half reactions work together. So I've got to multiply this 2 times 5, so I have 10, and this 5 times 2, so I have 10. So I've got to multiply everything on the top reaction by 5 and everything on the bottom reaction by 2. So that gives us the same number of electrons on both sides. So I end up with 5 oxalates, 10 CO2s, and 10 electrons. And the next one I end up with 10 electrons, 16 H pluses, 2 permanganates, 2 manganese ions, and 8 waters. And the key there was to get those electrons to equal, because that's the handshaking. Now the oxalate produces 10 electrons, and all 10 of those are used by the permanganate. And this is how we get the accurate ratio of permanganate to oxalate, because now we know it's a 2 to 5 ratio. If we didn't do that handshaking with the electrons, we would be off. We would say it was a 1 to 1, and that would be incorrect. It's a 2 to 5 ratio. So if we're doing stoichiometry, limiting reactant, titration math, we need to know that it's a 2 to 5 ratio. This is how we get that, by balancing those electrons. So now we cancel things on both sides, like the electrons, and we add them all together. So this is the overall balanced reaction. So everything on the left side of the arrow, 16 protons, 2 permanganates, 5 oxalates. Then they have the arrow and everything on the right, 2 manganese ions, 8 waters, and 10 CO2s, and the electrons have been canceled. Now, if we had waters on both sides, we would just take the smallest number of waters and subtract that from both sides. So it disappears from one side, and we have the net amount on the other. Let's check our charges. Okay, so we have a plus 16 here. So plus 16, minus 2, and then minus 10. So we have 5 of these, so minus 10. Okay, and so that's 16 minus 12 is plus 4. So 2 times plus 2. So that's fantastic. Our charges work. Then let's look at the atoms. 16 hydrogens, 2 manganese. Okay, where do we get 28 oxygens? Well, I've got 5 times 4 is 20, and 2 times 4 is 8. So there's our 28 oxygens. And 5 times 2 is 10 carbons. 2 manganese, that's easy. 8 times 2 hydrogens is 16. 8 oxygens here. 10 times 2 is 20. So 28 oxygens and 10 carbons. So this is, as far as balancing reactions go, these redox reactions are the most complex. I mean, now we're getting up to like 28 oxygens and things like that. You thought combustion was tricky, right? Where you just had the like 13 halves and you had to multiply everything by 2. And now that looks easy, right? But this has a procedure to it. If you follow the procedure, it's going to work every time. So everything checks out. Now that's the main content that I wanted to cover. So are there any questions in this process? Because this is the piece. Yes. Yes. Okay. Excellent. So let's go back to that. So I was right here, and so I'm looking at this, and I'm calculating. I got to figure out how many electrons to put into this half reaction. So I've got to get the charges on both sides to equal. So I see here I got eight positives, right? So that's the plus 8. You got that? and then I've got a 1 here, a -1 here. Okay, so 8 minus 1 is equal to 7, plus 7, okay? And then over here, I've got a +2. And I've got to get this arrow here, the left side has to equal the right. So I've got to find this +7. I've got to subtract 5 so that it'll equal +2. So that bit that I have to subtract is the number of electrons. So that's where this came from. It was I had 7 total charges on the left side, and I needed to get that down to 2. And you can only subtract, because when you're adding electrons, you're adding negatives. And so whatever side's higher, that's going to be the side that has to have the electrons on it. Yeah. And the same with the carbon. We get to this point right here. I got a 2 minus on the left and a 0 on the right. And so 0 is higher than -2. So I got to add 2 electrons on the right to get that 0 down to -2. So that's how we would know which side the electrons go on and how many we need. That only gets you to the half reactions. Then we get to this point here where we've got 2 electrons in one half reaction and 5 in the other, and we got to somehow get the least, what is that called? The least common multiple, so we've got to figure out how to get 5 and 2 to equal the same number. And it always works that you just multiply them by each other, 5 times 2 and 2 times 5. But sometimes it could be, I'm trying to think of another example where it wouldn't be just them multiplied by each other. Like if you had 2 and 4, you just multiply 1 by 2 and it equals 4. So you don't have to do anything to the one that has 4. Okay. Yeah. So these are the redox reactions that we use in batteries. So let's talk a little bit about batteries. We have volts and amps. Amps is current. That's how fast the electrons flow. But the voltage is how hard the electrons are pushed, okay? So you can think of this, the way I think of it is as a waterfall. So if you have a waterfall, let me draw a little mountain here, a little pool here, and you got a really thin waterfall of water falling down. And that might be like 1.5 volts, okay? And if you double the height of that waterfall, they add to each other. Okay, so it's not any wider, right? So it's not more water, it's just water falling twice as far. Okay, so it's hitting the ground with twice the force. So voltage is like elevation or height. Okay, it's like a potential, and that's what it's called, electrical potential. So think of potential energy as a ball on a hill. Electrical potential is, again, a ball on a hill. It's electrons being pushed. A higher voltage means they're being pushed harder. They have a higher potential. Okay. Current would be doubling the width of the waterfall. No more water per second. Okay. And so amp is a coulomb per second. So it's a charge per second. It's how many electrons are flowing per second. So if you have batteries in parallel, you're just able to deliver more current, but it's still 1.5 volts. So cells in parallel can deliver more current, but they'll be the same voltage. So 3, 4, or 5 batteries all aim the same direction can provide a lot of current, but they don't give any more voltage. Putting batteries end to end, you add the voltages. So if these are all 1.5 volt cells, you add 4 of them together, you got a 6 volt cell. Okay. So now you know why you have some things require like 1 AA and some things require 4 AAs and so on. It's just how much voltage that circuit requires to operate. Some of these batteries are really compact, and they have the anode and the cathode and the chemical reactants all in a really compact spot. Now that's great for portability, but it's also somewhat dangerous, okay? And that's what we're seeing in Tesla vehicles. Well, not necessarily the brand name Tesla, but in these electric vehicles, when they get water in them or some kind of damage, or even like some of your lithium polymer batteries, they'll just burst into flame because something damages the barrier between these. If this barrier gets punctured right here, then these things can react. and you've got the oxidant and the reductant, the oxidant and the fuel, if you want to think of it, real close together. And if you want to make this more and more compact, what do you have to do? You have to get those things closer together. It's called energy density. How much energy can I put in this small package? As we want our electric mobility to go further, we want more energy in a smaller package. And so the batteries are getting more and more dangerous. Okay, so that's why we're seeing these vehicle fires. You can't put them out like you can a fuel fire. So a fuel fire, you've got fuel and the oxygen is in the atmosphere. So you spray foam on that and the oxygen can't get to the fuel, and so it'll go out. So that's why, like, especially in aviation vehicles, you know, you have a plane crash, you have a huge amount of fuel, they come and they spray that foam over it, and so then the oxygen can't get to the fuel. So that's one of the advantages that like hydrocarbon fuels have over electric battery packs, is because it's harder for the whole fuel to start burning, and you can put it out if it does catch fire. So as batteries get smaller and you want higher power, they're gonna naturally get more dangerous. Here's an automobile battery, the sort of the classic one, the lead acid battery. It's a really interesting battery because if you look at the half reactions here, this top reaction produces 2 electrons. The bottom one consumes 2 electrons. And this is lead solid going to lead sulfate. And this is lead oxide going to lead sulfate. That's kind of interesting. And it's consuming sulfuric acid. Notice over here on the water, on the right, you just have water. So sulfuric acid is consumed by both of these half reactions. So that's kind of an interesting reaction. And so battery acid is actually one of the reactants. You have a lead plate with some spongy, it looks like waffles in there. And you have lead oxide in one plate, and then just a lead grid on the other, and sulfuric acid, and it'll deliver an enormous amount of current. So that's why we still use lead acid batteries, invented in 1859. But as far as the amount of current these things can provide, it's really good. So when you want to turn a motor, you've got to have a lot of torque. So you got to have a lot of current flowing through that electric motor to spin your engine and get it started. It was invented in the 60s. This was what caused the Apollo 13 to crash, or to have a problem in space, is they had these hydrogen oxygen fuel cells, and it was the oxygen system that failed. Okay, so this is old technology, but we're still working on it, because fuel cells would be great. Wouldn't it be nice to just take oxygen and hydrogen and flow them in as the reactants into this fuel cell, and you get electricity out, and the only effluent, the only thing that comes out of your battery is water. Okay. And they have there was a publicity stunt. I forget what city it is. I need to Google it again. Maybe you can Google it. And it was city buses that run on hydrogen oxygen fuel cells, and the mayor, to show that the effluent coming out of this bus was non-toxic, it was water, and they caught some in a glass and they drank it. Okay, I probably wouldn't have done that. I mean, no doubt it was pure water coming out of the internal guts of that fuel cell, but then it had to go through the exhaust system. How was that manufactured? That's the thing that I would be worried about. But it's pretty good. Now, in order to get high current, and again, that's high electron flow. Electrons are easy to flow through a wire. I mean, you can flow fast electrons, but protons, not so fast. And so this is the current limiting step, this proton exchange membrane. And so that's right here, this PEM, the proton exchange membrane, is the problem with this giving electric motors that have power that can push you along. I mean, we know how to make a fuel cell vehicle, but it wouldn't have a lot of strength. It wouldn't have a good acceleration. Okay. And I don't really want to drive around with a bunch of hydrogen gas in a tank. Okay. So that wouldn't be fun.
The city was Solaris.
Solaris? Okay, what state?
Sorry, it's Nanning in China announced they plan to replace their electric buses with the Solaris brand.
Solaris brand of
the
hydrogen fuel cells. Yeah. The other problem with hydrogen economy or hydrogen power is there's no hydrogen in the ground, in the air, or whatever. We live in an oxidizing atmosphere. So if a process produces hydrogen gas, the atmosphere chews it up. So we have to make the hydrogen. Hydrogen is an energy storage medium. So we would have to take water and electrolyze it. We would have to use electricity to do that and make the hydrogen, and then use the hydrogen to go back to water to give us the energy later. So that's another problem, is we have to actually make this fuel, so we can't get it naturally. Another use of electricity in these galvanic cells is to run them backwards, and then we can use it to plate metal out. So we can have like silver in solution or gold in solution, and we can put jewelry, and we can run this backwards and get that metal to plate out on the surface. So this is an example calculation with some things. So this definition of an amp is a coulomb per second. So that's one of your definitions. So when you see amps, it's a coulomb per second. And then 1 mole of electrons, this is the key here, 1 mole of electrons is 96,485 coulombs. Okay. And so with those two, let's see, where is it? Yeah, so 10 amps, 1 mole of electrons right here. That allows you to get out of moles of electrons and into moles of silver. So we have a mole of electron here, we got a mole of silver there. And so this problem is, what mass of silver can be plated on a piece of jewelry if it was supplied with 10 amps, so 10 coulombs per second, for 30 minutes in silver nitrate. So yeah, 30 minutes, 60 seconds in a minute, 10 coulombs per second. Then we have this conversion, it's Faraday's constant, of 1 mole of electrons for 96,000 coulombs. And then we can use the half reaction to give us the moles of silver, and then the molar mass of silver from the periodic table. We put 20 grams of silver on that jewelry. So this is how we do it, and this is how we calculate. We put X amount of coating on this item. We know the surface area of the item. We put it into an electrolytic bath and apply the voltage, and we can electroplate. Same with chrome plated bumpers, all kinds of things like that. We polish the surface. The state of the surface, that's what my research is in, is cleanliness of the surface and surface prep. And if it's a polished surface before you plate it, it'll be a polished surface after you plate it. So surface prep is the most important thing. We'll finish up with corrosion. So notice down here, I've added something to the activity series. Right between silver and palladium is this reaction of hydroxide and oxygen, okay? And so elements above that will react with oxygen and produce the hydroxide. So copper will push its electrons onto oxygen, and oxygen will produce the hydroxide. And so everything above palladium will react with oxygen and will produce the cation, and that's what we mean by corrosion. So the metal's corroding, it's being oxidized. Gold and palladium do not oxidize because they're below oxygen on the activity series. So you think oxygen can react with all metals, but it doesn't react with palladium or gold or platinum. Those are called the noble metals. And so they stay shiny. And silver will oxidize. If you have a silver set or silver glass or silver candlesticks or something, over time they turn kind of black looking, and it's oxidized. But it's a slow process because silver is not much above oxygen. But iron will oxidize pretty quickly. But notice where zinc is. Zinc is above iron. And so if we were to attach zinc to iron, then the zinc would oxidize and it would protect the iron. So this is what we do to protect iron. We used to have iron pipes, and then we would take zinc strips, and with just a hose clamp just below the ground, we would hose clamp some zinc strips to the iron pipes, and it would protect the iron pipes.
Just like your like on an outboard motor, you've got the zinc
Anode, yeah.
Anode.
Yeah, exactly. That's what you do, so especially in water.
It corrodes out before.
Yeah, and you can look at it and see. In the hot water heaters in RVs, you have an anode that you screw in, and then it will corrode and leave your tank in good shape. So these are the deep sea anodes. So, like you said, on your outboard motor, how big is that? It's about that big. Well, this is the leg of probably like a jack up oil rig. So this is going to be underwater in salty water and with oxygen and so on. So this is going to rust and eventually lose its structural integrity, and then the whole oil derrick is going to fall over into the ocean. You don't want that. Or you got a pipeline made out of steel. You don't want it to poke a hole in it, corrode, and then you've got a leak, a natural gas leak or oil leak into the ocean. So they put magnesium or aluminum or zinc blocks of metal onto those iron pipes, and that protects them. So this is what's happening with oxygen coming in and a water droplet, and even worse if you have like a chloride or something salty, it's going to chew into that iron. Sometimes you can get bacteria that will live on the iron oxidation reaction. So if you're all in a biology major or doing anything with microbiology, biology is a real problem with iron corrosion. Some of these little bacterial colonies will get onto an iron, and it'd be like they drill a hole right through the iron pipe. So a lot of times you've got to sterilize the water. Like if you have a fire protection system and it's a wet one, you've got water in there, you've got to put something in there to keep the bacteria from growing, because the bacteria can grow on this redox reaction. It produces energy that the bacteria can use to grow, and then it can divide and multiply. Okay. So how do we stop this? Well, we can put that zinc anode. And so if we galvanize, like sometimes we just plate the iron with aluminum or zinc, and then those metals will sacrificially corrode and protect the iron. So that would be what we do for corrosion prevention.
So with the zinc or like with the anodes, depending on what it was, have to be like changed.
Yeah. Oh yeah. So you would go down and you would have these deep sea divers. So a lot of the times, it's probably one of the most hazardous jobs in the world is an oil rig diver. They go really deep and it's super hazardous, and it's shark infested waters almost always, because you've got, I don't know, dozens of people living on this oil facility. And what do they do with the scraps? I mean, it's got food scraps, and the sharks and fish are eating the food scraps, and then you put a diver down there. And so then they go down and they have to weld underwater. So that's hazardous. So they can inspect those, they can weld on new ones. And it's one of those things that you're paid an enormous amount of money because of the high risk. But there's also the reason it's risky is, it's a risk of death. So, yeah. So you got paid a lot for a few years and then you died. So, yeah, it's a very, very risky business. So that's all I have for that. Those are some extra topics. Get busy on the next homework, because it's starting to get into solutions. So molarity and things like that. We're dissolving things in water and keeping track of how many moles there are per liter of solution.